Okay, we are live, so we can get started. Okay, good. So, the fifth lecture on the spectral methods module. So, the main topic of today's discussion will be what are called the Cheeger inequalities. We'll come to what these mean later. Let's do a quick revamp of today. We were working with, so just let's do a recall what we've done the last two lectures. We're working with this W, which is the random walk matrix. Random walk matrix. So it has this features that W is greater than or equal to 0 for. So let's for the purpose of this lecture, let's assume the vertex set is the vertex set P is just the numbers 1, 2 all the way up to n. So W has such that Wij is greater than or equal to 0 for all Ij. For all Ij in P, and W of 1 equals 1. 1 is a right eigenvector. That is for any vertex, if you sum its neighbors, the weights of all its all the edges leaving out of it, that sums to 1. That sums to 1. So these are the two properties. This is sort of a generalization of of D inverse A. So A is adjacency matrix as usual. Matrix, and D is the diagonal matrix corresponding to the degree of the vertices. That was D. This is a sort of generalization. This is one example of it, but a random walk matrix could be any such this one. Then while defining random walk, we had defined so there was a natural stable distribution or stationary distribution associated, which had this property that pi transpose W is pi transpose. Pi is a probability distribution. Pi is a vector from V to R. Pi of I is greater than or equal to 0 for all I, and summation pi I is 1. This was the random walk matrix definition. This is the stationary walk, the stationary. This one. Then we associate with an inner product. So we defined Fg pi to be summation pi I Fi Gi over I and B. We equipped it with inner product. This is a generalization of the natural inner product. Then we wanted to understand when do such random walks have a spectrum, a full spectral decomposition. For that, we needed to understand the notion of an adjoint. We had to look at what is the thing that satisfies W equals W star F G pi, and the adjoint was the random walk corresponding to the time reversal walk. And we saw that it satisfied the property that W star Ij was exactly Wji pi j by pi I. And this property, therefore, this let us define what are called reversible random walks, is those for which W star equals W. And for them, we do have the spectral decomposition. Self-adjoint under pi inner product. So these we had, so these were what we called reversible random walks, and reversible random walks. There was a full spectral decomposition. In particular, we had these so the eigenvalues, we had 1 equals omega 1 greater than or equal to omega 2 greater than or equal to omega n, which was greater than -1, and the corresponding eigenvectors, these were the right eigenvectors, where the all ones, this v1, v2, and so on up to vn, and the eigenvectors on the left are just pi, which is pi times v1, pi times v2, all the way up to pi times vn, where pi is just the diagonal matrix in which you put the stationary distribution on the diagonal. So this, and we also made a quick comment that for reversible random walks, pi w equals w pi. Therefore, w could be viewed as pi inverse of pi w, and this is a symmetric matrix. So this is sort of similar to D inverse A. D inverse A. So we will give me a random walk matrix. We will think of the underlying graph. The underlying graph will be one in which the edge weights are given by pi w. That is, Aij is exactly equal to pi I wij. Okay. And in this walk, what will be the degree of the ith vertex? The degree of the ith vertex will be the sum of the weights going out of the ith vertex, j. This is just summation pi I wij, and that will exactly be equal to pi I. The degree of each vertex will be its probability according to the stationary distribution, if you define the edge weights like this. And we saw a couple of consequences. Once you have this nice spectral decomposition, we saw a few consequences of this. We saw that the walk mixes fast. We saw convergence, and just a whole bunch of convergence depended on omega being max of omega 2 and minus omega n. And we then defined also the expander mixing lemma. These were two things which we saw last time. So any questions on this? Because the reason I sort of gave this long recap of last time is because we will need all of this for today's lecture. Any questions on any of this?
Yeah, I have. So in convergence, so is aperiodicity equivalent to saying that omega is greater than, so less than 1? Like we generally study aperiodicity as a requirement, right?
So we put aperiodicity as a requirement. That will be taken care of once you have the the smallest eigenvalue to be bounded away from -1 will take care of that. It will imply aperiodicity.
Okay.
Yeah. So aperiodicity is a more generic definition, but over here, if omega n is less than or equal is greater than -1, that implies aperiodicity.
Okay. And omega 2 not equal to 1 is for connectivity.
Is for the stationary distribution being unique.
Yeah. Okay.
Yeah. Okay. So,
Prahladh, can you recall what? So what was? I'm not sure I recall this. What was mixing supposed to be? or like mixing time?
Mixing is you start with some distribution. So there was a random walk. So you start with some distribution on the vertices, say possibly the point distribution for concentrated on one vertex, the point distribution and any vertex. And then you take a random step. You keep taking the random walk. Suppose the starting distribution was a stationary distribution, you will continue to be in the stationary distribution throughout. But now if you start with some other thing, you will keep changing the distribution. The question is what happens? You can ask if the eventual distribution actually becomes the stationary distribution. That's close. And mixing is, if you want to come within epsilon distance in some norm, say the total variation distance to the total variation. So it will tell you that if omega is bounded away in both sides, if omega is defined as the max of omega 2 and omega n minus omega n, if this quantity is bounded away from 1, then the random walk will eventually converge. No matter how you start, eventually you will get very, very close to pi. So you walk, you will eventually, if you take a few steps in this walk, which is determined by the second eigenvalue and the inverse of the stationary, the smallest probability in the stationary distribution. Depending on that, you will eventually, after so many steps, you will become very close to the uniform distribution of the graph.
Yeah, this was the proof that we saw last time.
This was the proof we saw last time. So expander mixing lemma. We didn't define expanders. Hopefully, expander was something in which just omega is bounded away from 1. Omega is something like 1 by 2, 1 by 3, or some such thing is called an expander. We didn't do it. But we saw what's called the expander mixing lemma. It just talks about if you take a random edge in the graph, and you have two functions f and g on the graph, on the vertices of the graph. You could ask for two quantities. One is you take a random edge in this graph and ask what is expected value of fg, where you are taking fu times gv proportional to the weight. This is taken as proportional to the weight of the edge, or you take expected f times expected b. This is assuming you don't have a underlying graph, but just take two independent copies from the stationary distribution. These two quantities happen to be very close to each other, and how close, that is once again determined by omega and the variance of the two functions f and g. And I just made it a remark, but this is very extremely useful, the expander mixing lemma, and hopefully we will see some applications of it in a couple of lectures from now. So what I want to today look at is, I want to look at the notion of a Laplacian, the Laplacian of the random walk. I want to study it a little. Okay. In fact, we will restrict our attention to reversible random walks because we know a spectrum only for them. So this is going to be this one. The way I'm going to define the Laplacian of the random walk is just going to be I minus W. That's how I'm going to define the Laplacian of. Notice in the case, for graphs, we had defined this to be, for graphs, we had defined Laplacian to be D minus A. D minus A. So I can write this as D into I minus D inverse A. And for walks, I'm calling this particular quantity the Laplacian. So sometimes this is also called, instead of calling it the Laplacian, it's called the normalized Laplacian because you're taking out D. But this is not, they use Laplacian sometimes to refer to, Laplacian is used to refer to this quantity, and normalized Laplacian, Laplacian is referred to this quantity and normalized Laplacian to this quantity. Sometimes people do this distinction, but I don't know if this is standard at all. So usually this is always, for a random walk, this is called the Laplacian. For a graph, this is called the Laplacian. There is a slight, this one over here, because in one case you have to take out D, other case you don't have to take out D. You should go by each textbook has its own thing. So for purpose of random walks, I'm going to call this the Laplacian of the random walk. Okay.
So usually what's the meta goal behind defining, what's the Laplacian in general for, like, what do we expect from it?
So what do I expect? That's exactly what I want to say. The Laplacian, I want the Laplacian to represent okay, now I have just defined the Laplacian this way as an operator. The Laplacian, the reason it's going to be defined this way is it refers to a very nice quadratic form on the edges.
Right. Yeah.
We saw that for the sake of graphs. I want to say, even for the sake of random walks, this represents. In fact, the quadratic form is precisely this quadratic form. Go over all possible edges. Look at the summation of. So what's a quadratic form? Quadratic form is some function on the vertices, some quadratic function on the vertices. So you're going to some quadratic function f on the vertices. Now, what's a quadratic form? Associates a real number to this quantity. What's a real number? It's a real number which associates to this function f. It associates the following value. Goes over all edges ij. Looks at the sum of fi minus fj, the whole square, weighted by the edge weight of that particular edge. It's this nice quadratic form. And what we will see in the next 5 minutes, what we'll see is this operator that I have defined now is the operator that corresponds to this particular quadratic form. And this quadratic form is a nice. And then we will, whenever I say Laplacian, I'm only referring to this quadratic form. This is what, and that's what so we'll take 5 minutes to, given this Laplacian, this matrix, an operator definition, we'll go to the quadratic form definition. And then for the rest of the lecture, we'll work with the quadratic form, because that's what I mean by we want to work with Laplacian. Okay.
Also, I mean, so in graphs, we had d minus a, where like d had a degree, or I mean, if you take the weight of an edge to be 1, then it was the sum of weights in the diagonal. I mean, in that sense, this is the same, because in W, the sum of weights is always 1.
Sum of weights is all.
It's a random walk matrix, right?
Yeah, in that sense, it is the same. But though W is not necessarily.
It's not not a symmetric.
Not a symmetric matrix.
Yeah.
It is the same in that sense. Yeah, it is the same in that sense. Yeah. For every W you are putting, it's the same in that sense. But I don't want to think of W as edge weights. The edge weights for a edge is pi I times Wij.
Yes.
That's what the edge weight is. So let's look at the operator. So what we want to do in the next 5 minutes is exactly, so why is the Laplacian a nice, this one? So we look at what the operator meaning of it is and what is the quadratic form corresponding to the Laplacian. We look at both of these corresponding to L. So that's going to be, this is what we'll try to understand. There's an operator. The Laplacian certainly takes functions on the vertices. The functions on the vertices, basically it's mapping f to LF. And let's just write this down. So LF of I, what will this be? This by looking at the thing, this is, I'm just writing the matrix definition. This is just J, Lij, Fj. But Lij looks of that form, so it will be just, in fact, if you stare at it, this will be just Fi minus J, Wij, Fj. And this, I will write it in a slightly fun form. I'm going to write it as Wij, Fi minus Fj. I'm just using the fact that summation Wij equals 1 when I sum over J. So the Laplacian is this operator. Okay, that's the operator. Now let's go to the quadratic form. So looking at FLF. But we'll work always with, now this will work with the pi inner product. So what is this? This is by definition summation over I, pi I, Fi, Lfi. Now I'll use the whatever we defined in the operator to write this down. This is summation over I, pi I, Fi, summation over J, Wij, Fi minus Fj. I'm going to open this out, bring summation Ij, it's pi I, Wij, fi minus fj. This is not exactly what I had promised you. I had promised you that the Laplacian form will be fi into fi minus fj. But I want to say I can read. I had almost promised this. I had in the beginning of said instead of this quantity over here, I'll have fi minus fj the whole square. Actually, this is equal to that. I'm just going to do a little manipulation more to this and show that the random walk because it's a random walk matrix. The wij is all ones is a right eigenvalue to it. Therefore, from that you will actually move this around. So I'll sort of do it in the sleekest way. You can sort of write it down otherwise also. Let's do it in this one. So I'm going to by the way, and I'm going to do this proof without assuming reversibility. This is going to be true for any Laplacian. The Laplacian has a meaning even for non-reversible matrix. It will always represent to this particular quadratic form. So let's look at this other. So let's look at. So FLF pi certainly can be written as FLF pi plus L star F pi by 2. The joint has this property. The joint is just this one, and so I can write this. So let's for now just write down what L star FF is. This is the same because of symmetry. This is the same as L star F. And L star will be just I minus W star. The adjoint of this is just I minus W adjoint. So this, by exactly the same calculations which we saw above, this will be pi I W star ij fi minus fj. But W star ij has the satisfies for any, not just reversibility, it satisfies that pi I W star ij, that was a definite, is equal to pi j wji. It satisfied this. So let's just use that. So I'm just going to rewrite this as ij pi j wij fi into fi minus fj. Okay. Now this is almost like the other guy, except it's almost like this quantity. It's symmetric to this quantity, except it had pi I wij. This had pi j wij. So what I'm going to do is just reverse the meaning of I and j. So I'm going to say ij pi I wij. Flip the I and j. Just what was I equal j. So then this is fj into fj minus fi. Okay. So that's 1. This is 2. So now let's go back to FLF. FLF, we had defined it to be half of FLF plus L star F. By definition, it is this. This is true for any random walk. But now you can, I calculated both this quantity and this. So if you notice this is exactly equal to half of summation ij pi I wij. In one case, I have fi into fi minus fj. Other case, I have fj into fj minus fi. If I add them both, I am going to get fi minus fj whole square. Fi minus fj is common, it comes out, and this is what it turns out. So the cleaner way to write this is not I power ij, is to write over all pairs ij instead of unordered pairs. The previous, and then drop off the 2. So this summation is overall unordered pairs. You can ask whether the element is it going to be counted twice, once, in ordered pairs? The point is really doesn't matter because it's fi minus fi square. It goes there. That quantity really does not contribute to it. So we're talking about distinct ij's only in the definition. So this is what we have shown so far. So let's write it down. So the proposition which I want to have. So for any random walk, W, this proof did not use reversibility. For any random walk, not necessarily reversible. For any random walk W, not necessarily reversible. The quadratic form corresponding to the Laplacian is this guy. FLF equals summation over unordered ij pi I wij fi minus fj square. And this is so why do we care about Laplacian? It's this nice energy function. So if you're done on fair amount of physics, this is sort of, if these are you can think of Fi's as potentials, pi I by wij as resistances. This is exactly I square R, sort of looking at the total resistance of that's why energy comes. So the Laplacian is something that will keep coming up, very common when you study networks and stuff. And it comes a lot in when you study networks. This one, it's the same definition as before. And it's an extremely nice quadratic form. Okay. So people with me on this?
Is this supposed to be useful in this? There's this electrical networks look at flows in graphs, right, or something.
This is the reason why electrical, you can take a flow for an undirected graph and view it as an electrical resistance. This is the equation which is responsible for it.
Could you please scroll up ahead? I just want to make sure I got the proof. There was this point where you flipped I and J, but Wij stayed without being flipped.
No, Wij. So no, I made a mistake over there in the previous step. So pi I Wij, this should have been
okay,
Wj.
from star to
this one. That was the definition of star.
Yeah, makes sense. Yeah.
You caught me. Yeah, that was great. So once again, notice that Wi. Once you look at it as this quadratic form, firstly, this is a quadratic. It's a quadratic form. It's always a non-negative quadratic form. The Laplace corresponding to Laplace, the Laplace is always non-negative. So it's almost a positive semi-definite thing, except for the positive semi-definiteness. We need for over reals. If you recall previous lectures from before, we also needed that the thing is symmetric. Over complexes, positive semi-definite. If it just was a quadratic form, if it was always a non-negative guy, we already said it was positive semi-definite. Here, the same thing will happen. So Laplacian is always the quadratic form is always non-negative because of the way it's written. If the weights are all positive, if Wij's are positive, which it is. If furthermore, for reversible random walks W, L star equals L. So it is its own self-adjoint. It's its own self-adjoint. And there, when we did it previously, we talked about matrices. We said that a matrix should be equal to its transpose. It should be symmetric. But now that was because we always worked with the usual dot product being the inner product. When you talk about something orthogonality, you have to, there's an underlying inner product, then the actual definition of symmetry is, it's not symmetric over there, it is self-adjoint is what was this one? L star, and hence, and L is a positive semi-definite operator. And when I say under some inner product, it's always under the inner product. Okay. From this, it should now be evident that what is the eigenvector corresponding to the minimum eigenvalue for F? What can be the eigenvectors all have to be non-negative, because the eigenvectors or eigenvalues all have to be non-negative, because by the Rayleigh coefficient definition, it is the quadratic form by FF by that definition. All eigenvalues, which are whatever they are, they all have to be non-negative. Therefore, in particular, the minimum eigenvalue has to be non-negative. I want to claim the minimum eigenvalue is actually 0. What's the corresponding eigenvector? It's the all ones. It's a constant eigenvector, will be an eigenvector corresponding to this. But this actually we saw, this is something which we don't need this theory. That is for reversible random walks. For reversible random walks, we already saw that W already had a full eigenspectrum, because we saw this, and L was just I minus W. Therefore, if omega is an eigenvalue for omega, if V and omega are an eigenvector eigenvalue pair for W, the same V and 1 minus omega will be an eigenvector pair for L. Therefore, its eigenvalues are exactly going to be, in fact, I'm going to write this in decreasing order. So lambda 1, which is equal to 1 minus omega 1, which is 0. This will be less than or equal to lambda 2, less than lambda 3, all the way up to lambda n. Let me actually rewrite this way. So the eigenvalues are actually going to be called 0, which is lambda 1. This is lambda 1. This is actually 1 minus omega 1, less than or equal to lambda 2, which is 1 minus omega 2. The eigenvalues are exactly the eigenvalues of the random walk flipped around. Lambda n, which is 1 minus omega n, and hence this is a number less than or equal to 2, because this was at most greater than or equal to minus 1. So the Laplacian's eigenvalues are all sandwiched between 0 and 2. The random walks matrix was between -1 and 1. This is 0 and 2, and 0 is always achieved. 0 is always achieved. The eigenvectors, as usual, it's the right eigenvectors I'm talking about, are the same as what we had for the same eigenvectors as we had for the random walk. Is this okay so far? Like that also. And what is the Cheeger inequalities I'm going to talk about? So last time we saw that the graph is connected if and only if omega 2 is strictly smaller than 1. This is what something we said. In this world, rewriting it to the Laplacian, this will just mean lambda 2 is greater than 0. Omega 2 being less than 1 means lambda 2 has to be strictly greater than 0. And you can notice this from the, it's also evident from the quadratic form. You know that the all ones is 1, the constant vector. So if anything has to be corresponding to the eigenvector corresponding to 0, it should be z. Then the corresponding, let's look at the eigenvectors which corresponds to the eigenvalue 0. When you stare at the Laplacian's quadratic form, the only guys corresponding to this will be the guys, it has to be constant on each component of the graph. Now, if there are multiple components, you do get that all those eigenvectors will be orthogonal to each other. In fact, you will get, all I'm claiming is the eigenvectors corresponding to the eigenvalue 0 are exactly those guys which are constant on each component. Therefore, if there's only one component, this will be exactly a one-dimensional space, and it will be the connected graph case. If there are multiple components, then the eigenspace corresponding to the 0 eigenvector will be exactly of dimension the number of components of the graph. So what we are going to do today is going to understand this concept. So this graph. So we're going to study something called the Cheeger inequalities. It's a quantified version, and it will take me a while to actually describe. It's a quantified version of this statement. The graph is connected if and only if lambda 2 is 0. And I will come, we'll spend the next 10 minutes trying to say what I mean by a quantified version. So we're going to come up with a notion which sort of captures connectedness. Was a Boolean property, if the graph is connected or not. It's a yes-no property. What we are now going to come up with is more a quantitative notion of how well is the graph connected. We're going to come up with a quantitative notion. So we're going to define what is called conductance. And by the way, the name is once again inspired by electrical engineering. It's the same. So conductance, which is a measure of how well the graph is connected. So let me start off by defining it for regular graphs, and then I will go on to extending it to irregular graphs, and then for any random walk matrix, we will extend the definition. So start off with regular graphs. Deregular. So firstly, I'm going to define phi of let S be any subset of the vertices. This is going to be del the number of edges that go out of S times. So let me first draw a picture so that before I do. So what we want to look at, so there's this graph G over here, and S is some subset of vertices S. What we are interested in is how well is S connected to the outside world. We're going to look at this. So dou S is going to represent the set of all edges. So all set of all edges ij, so that I is in S, J is not in S. Dou J represents to this quantity, dou S represents to this. And this is the number of edges that are leaving S. What are the number of edges actually? These are the number of edges going from S to its complement. But what are the total possible number of edges? Let's always think of S as a smaller size. The number of edges that can potentially go out of S are D times S. It's a regular graph. Those are the edges emanating from S. Not all of them necessarily go outside. Some of them possibly go back into S. So conductance is asking how well the graph is connected. You give me any set yes, how many of these edges are responsible for connecting me to the outside world, and how many of the, some of them are just connecting me within S, some of them are connecting me to the outside world. So conductance is this notion phi of S. So let's define it over here. Phi of S is size of dou of S by D times the size of S. So let's assume S is less than half of S is a smaller set. When I talk about a cut, we'll always refer to the smaller side of the cut. So notice this quantity is a nice quantity. What is it trying to capture? The numerator is the number of edges that connect S to its complement. The denominator is the total number of edges that go out of S. So this ratio is connecting what part of S is actually responsible for connecting S to its complement. So it's a measure of, for example, if there were no edges going out to its complement, this will be 0. So this is sort of a measure of how well S is connected. Of all the edges that are coming out of S, what fraction of them is responsible for connecting S to the outside, to its outside world. Okay, and the conductance of a graph, phi of G.
Minimum of phi of S overall is?
Yeah, it's a minimum of, it's the worst set. It's a set which observes the least of this. It's a minimum over all S. So minimum over all S, let's put that size of S is 0 less than or equal to 0 less than size of S less than or equal to size of B over 2 of phi of S. Okay, so that's the conductance of a graph. It's the worst, it's the set which is least connected to its complement, for which most of its edges actually are going back into it. So in particular, if a graph is disconnected, phi of g will be 0. Phi of g is really defined 0. Now let's just extend this definition to irregular graphs. So there I'm going to define dou s. Dou s, this quantity, I'm just going to write it as summation of all w, summation of all aij, I in s, j not in s. So I'm just going to count. It's the same notion. So actually irregular, so let's do it in steps. Let's do it first for irregular unweighted graphs and then eventually extend it all the way to weighted graphs also. Irregular unweighted graphs. Dou s will mean the same thing as before. Dou s is set of all ij, I in s, j not in s. And the denominator, instead of putting d times s, what you'll have to put is a total, so the sum of all the edges that go. So the denominator d of an s, we'll write it as summation degree of I in s. These are all the edges that go out of, these are all the potential edges that are leaving vertices in s. So in this case, phi of s is going to be defined to be size of dou of s by d of s for s such that d of s is less than or equal to d of v by 2. It's the one which has a smaller degree compared to the total degree is d of v, the sum of all the degrees. And I want to look at this. Should I look at set yes or should I look at v minus s? And this I'm looking at set yes. So this is how I will define it for irregular graphs. Okay. And once you define it for irregular graphs, now you can go all the way to this one for general weighted graphs. Weighted graphs, phi of s, I'm going to define it to be just dou of s by d of s, the same definition, where dou of s now just refers, dou of s is going to just refer to the weight of all edges, sum of the weights I in s, j not in s. That's going to be the sum. And d of s is summation over all I in s, and furthermore what? It's a summation over all j in the vertex set of aij. It's the degree of that vertex. Okay, these are natural. So once we have this, so this is what I'm going to define as, this is what we'll define as conductance, and the conductance of a graph is just phi of g is the minimum of this quantity, minimum over all s, such that 0 less than d of s less than equal to dv by 2 dou s by d of s. People with me? Notice that this definition can be extended to a random walk matrix also, a reversible random walks. We'll just define, take the edge weights coming from the underlying graph and then define the same quantity. So now this previous statement, this statement that G is connected implies if and only if lambda 2 is greater than 0. This turns out to be phi is greater than 0 if and only if lambda 2 is greater than 0. This is the same as this statement. Because G is connected is stating that phi is non-zero. Okay, this was the original statement. Now what we will say is, so Cheeger inequalities are sort of the Cheeger inequalities. is a robust strengthening of this. It says that I give you phi of g. If phi of g is small, so is lambda 2. If phi of g is large, so is lambda 2. That is, if this is small, that is small. If that is small, that is large, this is large. So it's a quantitative strengthening of this is what is called. It's a very important. This one, so let me actually give it a completely different color. These are what are called the Cheeger inequalities. So it's in some sense a strengthening of the previous statement. The previous statement says if lambda 2 is non-zero, phi is non-zero. And this tells you not only that, if lambda 2 is small, phi is small. If lambda 2 is large, phi is large. And it's a quantitative version of the previous statement. It's a very important thing. This was discovered and rediscovered multiple times. This one, Cheeger, it's called Cheeger because actually it's Cheeger discovered in 70s in the context of manifolds. Not in this language at all, not in the language of random walks. But if you come to graphs and random walks, this was discovered and rediscovered several times. There was Jerom's in the 80s. This was in multiple papers. People discovered. Jerome Sinclair defined it, proved it once. Alon Millman, Lawler and Sokol. Varopoulos. Dodzik. Yeah, did it in the 80s. And more recently, I think they found out that actually there's an old paper by Polya and Sego from the 50s, which also has a version of the Cheeger inequalities for random walks. So this is something which appears a lot of times people independently discovered, and now it's become a standard toolkit in the Markov chain literature. Cheeger inequality is measuring the conductance. It's a quantitative feature of the conductance, and it's been done twice. So once, if you want to show how well a graph is connected, you compute its second eigenvalue and say the second eigenvalue is separated away from 0, or you say the graph is very well connected because phi of g is significantly large. It's also being used in the other direction. Sometimes you need it to know what the second eigenvalue of the graph is. And the graph was not a nice graph to work with. So instead, what they show is we'll actually compute the conductance of a graph. We'll show that how well the graph is connected. That gives me phi of g, and that is large enough. And that tells me that lambda 2 is separated away from 0. If phi of g is large, then lambda 2 is also large. So it's been used in both directions. And we will see the proof of both directions shortly. Today we will actually, just one second. Today we will see actually the proof of this. We'll use Fan Chung's presentation. Actually, the one which I will use is a presentation due to Girish, who was a student over here. Yeah, this is the presentation which we present in class. Yeah, go ahead, Varun.
So this notion of connectedness that we get due to psi is this related to like the k connectedness, that the graph is k connected if you have to remove k edges before it's disconnected.
So this is not k. This is not k. K connectedness is still. This is not. So this is not k connectedness. K connectedness is related, but it's not the same problem. This is just telling you. This is just telling you what give me a set. What fraction of its edges? So edges coming out of this set. What fraction of edges arising from this set are responsible for connecting it to the outside world? So it's this ratio. It is not the number. There you care how many things are there in that set. Is it 1? Is it 2? Is it that is? Can you make a graph disconnected by removing 1 edge, by 2 edges, by 3 edges? That's what. There you're only caring about the numerator. Here I want to say it's not the numerator. I want to care about this ratio because it's in some sense it's unfair to compare a singleton set versus a large size set, because a singleton I can certainly disconnect it from its neighbors by removing all its degrees. So in that sense, k connectedness can never be larger than the degree of a vertex.
Yeah.
Huh? But I want to have a same notion of connectedness for sets of all size. Therefore, you're normalizing that notion by the size of the set or the number of edges that potentially leave that set. That's the denominator. So this is more a normalized version of K connectedness. K connectedness, we are only looking at the numerator. This is something, and this will cause issues later in the sense of when you're looking at combinatorial optimization problems, just the fact these two will become two very different problems to find this. Yeah.
Okay, because what I was wondering is when like psi g can be at least as of now it can be at most 1, right?
Which one?
Psi the connect psi can be it's 0.
So
It means
phi can be at most 1. The way phi is a number between 0 and 1. Phi is a number between 0 and 1.
Yeah, so I mean, what I was wondering is like as phi grows from 0 towards 1, does it have any relation to general connectedness? Oh, we'll see.
It could. I don't know if these two are related things, but it could. You could sort of do this. So phi is sort of measuring. The phi is stating that phi of a set, yes, is talking about how many edges responsible, how many edges that leave out of this are responsible for connect. What fraction of them are connected to the outside world? Several of them could go back because several of them could go back inside. It's asking what fraction of this. That's what phi of S is connecting. And phi of G is the set which has the worst such conductance, is phi of G. Okay. So let's go into the proof of Cheeger. So proof Cheeger is usually, there are two inequalities we have to prove. There are two things which are, one is called the easy direction and the hard direction, and you will see why the proof. The one proof will be very simple, the other proof is fairly involved. The easy direction will be showing that if the conductance is small, even if the conductance is small, the second eigenvalue is small. Sort of stating that small conductance implies small second eigenvalue. In fact, we'll prove a stronger statement. The way we will prove this is by proving this stronger intermediate fact. We will show that you give me any set, yes, with a particular conductance, we will show that lambda 2 is always small, lambda 2 by 2 is always smaller than the conductance of this set. For any set, not just the minimum, for any set, yes, subset of vertices. Let's assume that size. Let's assume that size of S is, let's any set yes such that d of S is less than or equal to d of B by 2. Actually, should I write it in this language? Let me just take a pause. I'm going to write it in d of S. So we're going to prove everything in the random walk. So this is pi of S is less than or equal to half. In this world, d is just going to be the sum of the, it's going to be just pi of S. The degree in a random walk is degree of every vertex is just the probability that the transition, probability that the sum of the edges weights gives to it, which is exactly pi I. We did this at the very beginning of the lecture. Let's just recall this. We did this over here. Write this set of inequalities. So if the underlying walk, if it's a random walk and this is the edges I give to it, the degree of a vertex is exactly pi I we saw. Degree of a vertex is the sum of weight of the edges going out of it, summation j aij, which was summation j pi I wij. Now wij sums to 1, therefore this is the degree of a vertex in this random walk is just pi I. So we'll work with the random walk definition and prove all of this that way, because that includes all the cases, regular, irregular, weighted graphs, everything. So for every set SW pi S, we'll show that phi of S is actually greater than or equal to lambda 2 by 2. That would be the easy direction. And prove using the Courant-Fisher characterization of So I have given you a set which is whose conductance is low. From this set, I need to show to you that the eigenvector is low. So what's the Coran-Fisher stating says lambda 2 is the minimum over all x orthogonal to the smallest eigenvector of the corresponding Rayleigh coefficient x, Lx. So let's actually not use lambda x, let's use f. I know. Okay. That's going to be, we know this. So all that we need to show is give me you have given me a set S. From that set S, which has very little conductance. From that set, I want to pull out a F orthogonal to the all ones vector and show that the corresponding Rayleigh coefficient of F is small, which will, because lambda 2 is the minimum of all such Fs, lambda 2 will only be even smaller. So what's a natural choice for this F? I give you a, so we have, so let S be some subset of, let S be a subset of the vertices such that pi of S is less than or equal to half. It doesn't, the total weight of S is not more than half. So what is a natural thing? There's one, I want a function of the vertex.
F is 1 on S.
Yeah, so the natural choice is, so one natural choice is the indicator function of S. So let's actually look at what 1S, L1S is. This was the numerator of this quantity. This, by definition, this is just summation over all ij, pi I, wij, 1si minus 1sj whole square. Now this quantity within the square is either 0, 1 or minus 1. It's 0 if I and j are on the same side of the cut. And it is 1, it's 1 or minus 1 depending on whether I and j are on, by the way, this is over unordered pairs. If I and j are on different sides of the cut, it is 1. Therefore, this contributes exactly 1 when the I and j are on different sides of the cut. And that time, what does it contribute? It exactly contributes the size of the cut. This is exactly dou of S. That's the edges of all edges. Every edge in the cut is being contributed with its weight, which is pi I times wij. So this is great. This is in fact the numerator, which I have to put. So this was the conductance. The conductance numerator is this. And this is also a nice quantity. What is 1s? This is in the pi now. 1s pi.
What is this? It is like the quantity that we want, but then we are going over all unordered pairs, right? So
no. In the inner product, the inner product, this is just 1s of I, 1s of
pi s of I. Oh.
So this is just pi of S. It's just pi of S. I in. So it is, in fact, this ratio is exactly the ratio we care for. The numerator is dou of S, the denominator is pi of S, which is the degree of S.
Okay, yeah.
So you get it, but then I would have got lambda 2 is less than or equal to phi. But I put a 2 over there. The reason is 1s should be orthogonal to the all ones function. Unfortunately, 1s is not, or this is true only if 1s is, you have to, if you look at the Rayleigh, this one out here, we have to put an f which is orthogonal to the all ones function. It's not good enough to put any f. So the second eigenvalue, you have to put the smallest eigenvalue, you can do this. The next smallest eigenvalue, you have to go choose only f which are orthogonal to the all ones. to the eigenvector corresponding to the smallest eigenvalue. So this almost gives this, but it does not, because 1 is not. So however, all I want to say is, however, 1s is not orthogonal to the all ones. So what we'll instead use is, we'll use f, which is 1s, minus, we'll subtract, shave off a part of 1 so that it now becomes orthogonal. That is, basically we are going to take off the component in 1s which is along the all ones thing, so that now we'll only use the part of 1s which is completely orthogonal to 1. So what component do I have to use? I have to use it. I know I need I need f to be orthogonal to the all ones in the pi norm. This will state that 1s minus sigma 1 in the pi norm should be 0. So the first one is just pi s minus sigma times 1. So this should be 0. Therefore, sigma, and that is, sigma should be equal to pi s. So we'll set, so use f equals 1s minus pi s times the all ones function. That is going to be the f we will use instead. Okay. So now let's go back and compute for this f what is the Rayleigh coefficient. Are people with me why I'm doing this? 1s is the most natural choice to do, but unfortunately it has the, in fact, and it's very nice. It's the numerator denominators match out very nicely, except for the fact it's not orthogonal to the all ones thing. So now I'm shaving off from it the component along the all ones to get this. So now f is orthogonal. F is, satisfies f is orthogonal to the all ones. Let's look at what is FL F pi. So notice FL F pi is just, f is just a translation of 1s. Every quantity in 1s is moved by an additive term. That's how I defined it, because it's minus sigma 1. This is unaltered. This is the same as 1s L 1s pi. Because if you look at the quadratic form of it, as long as the difference of the two quantities is the same, it didn't matter. So whether the difference in the 1s world or the f world, the difference between fi and fj was always the same. You added the same additive constant to every vertex. Are people with me on this? So this is, I'm just using, this is true only for the Laplacian quadratic form. Laplacian quadratic form has this, looking at the Laplacian quadratic form, where is that? So it's this quantity over here. So I want to claim that FLF to every f, if I add just the same additive term, this only depends on the difference between fi and fj. And that is unchanged from going from 1s to f. 1s to f, that was unchanged. Since f is actually 1s minus sigma 1. It's because of that, this is true. And for this is actually equal to, the numerator is the same numerator which we wanted. But let's look at the denominator. Let's look at FF pi. What was this? This is 1s minus pi s 1, 1s minus pi s 1 pi. This is 1s pi minus, actually minus, open this out, this will be minus 2 pi s 1s pi minus pi square s 1 pi. What is this? This is exactly pi of s. If you write this down, this will be this quantity itself will be pi of s. So this is minus 2 pi of s.
Won't that be a plus pi square s?
Which one? Yeah, this is a plus.
Plus
Pi square s, and this is a 1. Therefore, this is exactly pi of s minus pi square of s, which is pi of s into 1 minus pi of s. So the Rayleigh coefficient, so let's do this. So we have lambda 2 is less than or equal to f LF pi by ff pi this was exactly dou s. This was pi s into 1 minus pi s. But pi s is less than or equal to half. Therefore, 1 minus pi s is always greater than or equal to half. Therefore, this is a quantity less than or equal to dou s times pi s, which is 2 phi of s. This is the easy direction. This is similar to the expander mixing lemma. We just had a particular set, we just wrote it down in the eigenbasis, and that was end of story. Are people with me over here? And in fact, this is the reason why, by the way, because of this proof, sometimes conductance is also sometimes defined as which we will not use, sometimes defined as phi of s is, I'll write it only for the regular graph case. It's d times dou of s by d times size of s into size of v minus s. If you write it this way, then this you would have stopped at this part of the proof. What did I do? You would have stopped at this part of the proof, because this quantity will exactly be this. It will be dou s times pi s will come from here. 1 minus pi s will come from there, if you have defined conductance this way. But the difference between this notion of conductance and the other notion of conductance is off only by a factor of 2, because we only consider a smaller size set. The other thing will only be a factor of 2. So this sometimes defined as won't use in our lectures. And the reason it's sometimes defined this way is because this proves that this quantity appears naturally. So in this, if we define it this way, conductance lambda 2 will be less than or equal to phi, period. There won't be that hanging factor of 2, but the hanging factor of 2 is it's better to define conductance the other way, because that has a more nice meaning. This also has a nice combinatorial meaning, but we'll work with the way we define conductance. The only difference between them is each of them is within another by a factor of 2. So it really does not matter much. Okay.
Right, so there is the d is there both in numerator. I mean, it's redundant.
The d is there in the numerator and denominator. So why did I put in the denominator? So 1 second. So I want to put it in. 1 second. I want to put it in the numerator. Sorry, I will not have to put a d. I will have to. So the way to define this will be. Okay, what I wanted to do is this way. I have to put d of s, the total vertices going out of s, the total vertices edges going out of v minus s, the total vertices going out of all the edges on the top. That's a fixed constant. You have to write it. That's just for normalization purposes. That is, I want to be comparing the same quantity in the numerator and the denominator. It should be scale in. This should be a ratio. It should not have a, what do you call it? This is a ratio. It should be a dimensionless quantity. Conductance is a dimensionless quantity. Okay, but anyway, this is an alternate definition of conductance you'll find in some books. That's not the point, but let's go back. Now let's go to the hard direction of Cheeger. Is the easy direction okay? And it's the most natural thing one would do in the easy direction. That is, you give me a set, yes, I will actually use the Rayleigh coefficient characterization of the second eigenvalue to demonstrate a particular vector orthogonal to the minimum eigenvector, which observes a small Rayleigh coefficient. And hence, if it observes a small Rayleigh coefficient, the second eigenvalue can only be even smaller. Okay, so hard direction. Now we want to show that phi g is less than or equal to 2 lambda. So what does this say? It says if you give me a small eigenvalue, then there is a cut with small conductance. If the second eigenvalue is small, then there is actually a cut which for which most of its edges are actually going into it rather than going out of it. And we'll actually give a constructive proof. You give me a second eigenvalue, an eigenvector. So in fact, the way we'll prove is a very strong statement. You give me a vector orthogonal to the all ones, which has small Rayleigh coefficient. So in particular, the second eigenvalue is small. That means from this vector, from the belly of this vector, I will extract out a set S such that the conductance of that set is really tiny. So we will prove this stronger. So you give me a vector which shows that the second eigenvalue is small, which demonstrates the second eigenvalue is small. What is it? You give me an f, a function f on the vertices. The function f on the vertices has the property that it's orthogonal to the all ones, and its corresponding ratio of the Rayleigh coefficient. Its Rayleigh coefficient is small. It's x transpose LF by f transpose f LF by ff. This is a small number. It's not too large. An f which witnesses this. From this f, from the belly of this f, I will extract out a set S, for which most of the edges actually go inside rather than go outside. So we will prove this. So the proof will actually be constructive. The proof, all I'm saying is the proof which we will show, the proof will be constructive. That is, given a function, given a f from V to R, such that 1, f is orthogonal to the all ones. So it's a cap. And furthermore, this, let's call this function ff by ff by, say this is some rho. And rho is small. So if rho is small, this is a witness to the fact that the second eigenvalue is small. Second eigenvalue is only going to be even smaller than this. Will construct a set S of vertices. One such that firstly pi of S should be half. We want to, it's a smaller side of the cut, and phi of S is less than or equal to, in fact, what will we show? We will show it is less than or equal to, we will show a slightly stronger statement. We'll show that it is smaller than square root rho times 2 minus rho if rho is less than or equal to 1, and it's 1 if rho is greater than 1. This is trivial. If rho is greater than 1, I'm just saying conductors is less than or equal to 1. That's a trivial statement. I only care if this Rayleigh coefficient is less than or equal to 1. What can I show? And we will show in, and this statement will imply the lemma which we want, because I'm going to prove a stronger statement. Is this clear? But the plan. So we will give a constructive proof of this. You give me a vector orthogonal to the all ones, which demonstrates that the ratio of the Rayleigh coefficient, the Courant-Fisher characterization is small. It demonstrates that it's a witness to the fact that second eigenvalue is small. From the belly of that vector, I'm going to pull out a set which has this feature. Okay. And
how is this a stronger formulation?
Why is this a?
Why is this a stronger formulation? Like we wanted to show that it is less than or equal to square root of 2 lambda 2, right? I mean, it's the second.
Yeah.
But lambda 2 is less than or equal to rho.
No, so I'm showing it's not only less than or equal to 2 lambda 2. I'm showing it's so. No, so in particular, if you put f to be the second eigenvector, then rho is equal to lambda 2.
Yes.
Yeah. So if you put the second eigenvector, you get rho equal to lambda 2. So if I get phi of s less than or equal to lambda 2 times 2 minus lambda 2, which is better than what I had promised.
Okay.
So all I'm claiming is you tell me a vector which has low Rayleigh coefficient, this Courant-Fisher characterization. From that vector, I will show you a set corresponding to that row. It will be small. And if that vector happened to be the second eigenvector, then this will give you the statement that I wanted. give me any give me any vector, not necessarily an eigenvector, for which its Rayleigh coefficient is not too large. From that eigenvector, I'll show hidden in that value of that eigenvector is a set S, which shows that the conductance is not too large. If I had set this F to be the second eigenvector, I would prove the hard direction of Cheeger. Does that answer you, Ishan?
Yes.
Yeah. So what is this going to be? So it's going to be fairly natural what we are going to do. So let's look at, so I don't have much time, so I'll set it up. I'll set up this one and we'll do the proofs next time. So F is a function V to R. So let's plot. So F is going to have both positive and negative values because F is orthogonal to the all ones function. F can't be all positive or all negative. F has to be, F is a non-zero vector firstly. That's another thing I need. F is orthogonal and so F is non-zero. F is non-zero. F is not trivially zero. In fact, that is necessary. Otherwise, this ratio is undefined in the next step. So let's look at how it goes. This is 0. So F has some value. So let's now relabel the vertices such that F's values are in, what do I want to say? The F1 is the most positive value. F2 is the next positive. Let's relabel the vertices this way. I'm just relabeling it so that up to a particular point it is Fs, and then it becomes Fs plus 1 all the way up to F. Just relabeling of the vertices. Just relabel vertices. Such that it looks like this. Now I want to pick, I have to pick a set of size smaller than half. That's what we need to do. So notice that each of these vertices have a corresponding weight. That's the number of edges going out of them, pi 1, pi 2, pi n. You want to choose certain set certainly which is less than half. So by the way, if F is an eigenvector with a particular Rayleigh coefficient, minus F is also the same eigen. It also has the same Rayleigh coefficient in this one. So we will set it up such that this part, the one above 0, this what I call this, that is pi of set of all I such that Fi is greater than or equal to 0. That's less than 0, greater than 0. We'll set it up such that pi of this is less than or equal to half. If this were not the case, I'll just flip F and put the other direction. One of the two sides has to be less than or equal to half, either the part greater than 0 or the part less than 0, and I'm just going, I'll flip F so that this happens. So I want to claim, so now F looks like this. And what we will show is some subset of this, just this 1 to S, is going to be our cut S that demonstrates it. In fact, what cut? We will actually show one of these. We will show that one of these cuts, that is either this set and it's this one, or one of the threshold cuts, either this set and everything else. This will be, we will demonstrate this. Give me F. We'll lay down F on the real line in increasing order. Just relabel the vertices. So we're going to pick those. Give me F. I'm going to line up F, write F on the real line. F is a mapping of V to R. So it is actually a mapping. It appears both on the positive side and the negative side. One of the sides has to be of weight less than half. Let's assume that the positive side is less than half. Otherwise, we just flip F. And we'll show that one of the sets of this things in the positive. One of the sets, there could be actually exponentially many of such sets because this one. In fact, I'm saying only of the threshold cuts. I'm just going to cut. I'm just going to draw an arbitrary line and choose all vertices to the left of it and all vertices to the right of it. That is a cut. That cut will actually demonstrate this. Okay, that's what is going to be our proof. So I'll state the two lemmas that will go into the proof, and then we'll prove the lemmas next time.
Just a small question. So this threshold zero, is actually arbitrary here, right? I mean, it need not. It can be.
The threshold 0. No. The threshold 0 plays a role. I know things are there on this side and that side precisely because F is orthogonal to the all ones. That's where I'm using F is orthogonal to the all ones. Okay, because otherwise, if I didn't have that, I could have worked with the same. The point you'll see it in the proof. You'll see the two things in the proof. So what I'm first going to, it is in some sense arbitrary, but so we're going to define a function. So I'm going to define something called. I'll call the function g going from v to r is a proper function if the following two is satisfied. G of I is greater than or equal to 0 for all I in vertices. It's a non-negative one. So in particular, f doesn't satisfy. F is not proper. If you give me the second eigenvector, that is not proper. And furthermore, pi of the total weight of all I such that gi is greater than 0. This quantity is less than or equal to half. That is, it gives non-negative quantities, but it doesn't give non-negative. It doesn't give positive to most of them. It only gives positive weight to less than half the fraction of the things. Most of the others, it actually gives 0 weight. That's what I mean by G being proper. This proper is a, I don't know what's a, we didn't have a name for it, so I'm just calling proper. It's some special function with this property. So that's what I'll call by proper. The first lemma I'm going to say, here I will use. So there exists. So given f, given non-zero f, such that f is orthogonal to the all ones and rho is equal to f lf pi, ff pi, there exists a proper G such that GLG pi is GG pi is also less than rho. It goes even smaller. So G is also vector. Only thing is G. The nice thing about G is G is a proper. It gives non-negative quantities to everything, but more than half of it gives the value 0. So the way we'll define G will eventually be take f, all the negative quantities, make it 0. That's going to be G. We'll see the proof of this. Why that G is proper, we'll see next time. It's just f to G translation is just going to be take the original f and just replace it with which it's a, on the positive side, it's a G is the same as f. On the negative side, G is just 0. You just zero out all the coordinates values. We'll show that this is proper. That's lemma 1. Lemma 2, which we'll show, is if G is proper, then phi of G, phi of the graph G, is always less than, if G is proper, then it's less than or equal to rho times 2 minus rho, where rho is actually the Lele coefficient corresponding to G. Yeah. Okay. This is what we will show. So the conductance of a graph will only be smaller. In particular, we'll demonstrate a set S. Demonstrate a set S. And notice that if you put these two together, we will be done with the proof. Okay. And that's what we will do next lecture. Any questions on this? Otherwise, we will stop. Okay. Let me stop the